is one of the persons who formed the nucleus at the time of formation of the CMS experiment, and also he was crucial in taking along the Indian groups in this collaboration. And he has won many accolades, including the Fundamental Physics Prize, Breakthrough Prize for Fundamental Physics, Panofsky Prize. And with that brief introduction, I request Professor Virdi to give his talk.
Thank you for the introduction. Can you hear me?
Yeah, clear.
Okay. We'll switch off my video so it doesn't saturate the bandwidth. Let me thank you all for this kind invitation. And so I will go and present a view. Can you see my slide?
Not yet.
Can you see it now?
I see you only. Camera is on, not the microphone, and not the screen.
Sorry, let me just try something else. Go full screen. Can you see that now?
No, not yet.
Oh. Okay, so let me try that now, and I'll go there. No.
Yeah, I think it is coming now.
Fine. Okay.
Let me just stop and start again. Can you see that now?
Yeah. Yes.
Full screen?
Yes. Fine.
Is that okay now?
Make it full screen.
Is that full screen?
No, we see the side screen also. This two screen coming.
Okay. Let me just go there.
Yes. Yes.
Can you see that now?
I think this is right.
Can you see the screen?
Okay.
Yes, Jim.
Now it's perfect.
Yes, it is okay.
Okay, let me do that. So let's you can see that now, right?
Yes.
Yes,
Okay.
please go ahead.
Yeah, so I was asked to speak about the finding the Higgs boson, so I'll try to give the first part, which will be applicable to both CMS and ATLAS, but then I'll concentrate on CMS and also bring out some of the issues in the construction of these experiments. I know there's much better, but many of the things I will talk about are applicable also to ATLAS. And I know you've had talks earlier on the theoretical and the experimental aspects of the discovery of the Higgs boson, so I will not talk much about that. Now, but I will say that, as you all know, the LHC allows us to probe our universe about a few picoseconds after the Big Bang, and as you all know, about 1/10 of a nanosecond after the Big Bang, a phase transition took place in the universe, which meant that the fundamental particles like electrons acquired mass, and the mechanism, as you all know, is the Brout-Englert Higgs mechanism, which postulates that there's a field that pervades the universe, and the quantum of that field is the Higgs boson. So now what I'll start by talking is starting with the physics drivers, because in the end, when we design experiments, we design them to discover the physics we want to do. And the instruments we choose, or the subdetectors, are meant to do that job. So it's not something which is nice to do. It is driven by physics. So the physics drivers for the detector design, the questions with respect to the hadron colliders, in fact, which is this is a slide from the early 1990s. And there are about 5 questions which we were trying to address. So this is a copy of a slide which I used to show in the early 1990s. And you know all of these things. The standard model contains too many arbitrary features. And one of the main aims was to clarify the electroweak symmetry breaking sector, which is the Higgs mechanism, or the mechanism that gives mass to fundamental particles. At that time, we said the answer will be found at the Lhc energies, and we have found it, so there's a tick there. Now, also, I think has been alluded to, the Standard Model gives nonsense at the Lhc energies, in the sense that the probability of some of the processes becomes greater than 1, which is W left scattering. Now, a Higgs mechanism or ground-angulated Higgs mechanism does provide a solution, but we need to actually experimentally prove that. We haven't done that. Hopefully, we'll be able to do that in the next 10, 15 years. Now, the other things are to identify particles that make up dark matter. So already at the early 90s, we knew that even if the Higgs boson is found, all is not completely well with the Standard Model alone, because one of the first questions that crops up is, why would the Higgs mass be so low? Because it does corrections, which floats it up to the next scale up. Now, it was conjectured that there'll be a new symmetry, supersymmetry at low energy, which would then address this problem, and that it should show up at the Lhc energies. It hasn't happened yet, although I think most of us are expecting that to happen first and then find the Higgs boson. The other thing also you're aware of is the Higgs this search for new physics of the TeV scale. The TeV scale is rather special, but we also know that the Standard Model is logically incomplete, and it does not incorporate gravity, as we all know. And so it has some dramatic concepts which come up, which are supersymmetry, extra space, time dimensions, and so on. So let me then go to the Higgs boson itself. It did serve as a very, very important benchmark in trying to design the experiments. And the reason is that although the mass is not known, but once the mass is fixed, everything else is known about the Higgs boson, the Standard Model Higgs boson. So you could use that, and it has very different decay modes depending on the mass, and its width is also quite different depending on mass. So at the top, you have the natural width, and then you have the bars. And this is again a slide from the 1990s. And the bars actually represent what we thought at that time that would yield a 5 sigma discovery with 100 inverse femtobarns at root S of 14. Now we know that we found the Higgs boson with something like 20 inverse femtobarns at half the energy. So obviously the experiments have done better than we thought. Now, as you notice, where we eventually found it, only the Higgs to gamma gamma was considered to be something that was possible. Even the ZZ star, people felt that it can only go down to about 130 GeV with that condition on in the red box. And then, as you went up in mass, you have to look at other more larger branching fraction modes and bringing in neutrinos and jets as such. So the fact that we found it this mass here meant that there was a considerable emphasis being put on the gammas and the electrons and the muons. It was also felt that, or people were telling us, the low energy supersymmetry gave some sort of a upper limit on the mass of the Higgs boson at the level of about 135 GeV, if I remember correctly. So that meant that this area had to be really looked at very, very carefully when you're designing the experiments. And that put the emphasis on the requirements of tracker momentum to be very, very good, and the ecal electromagnetic energy resolution to be very good. So a lot of effort was put in there, and I will indicate that as I go along. Now, so what other things were important? Now we've done the Higgs boson. So the other thing was this low energy supersymmetry that I mentioned. And on the right-hand side, you'll see a very complicated decay chain of one of the points where supersymmetry could lie. And you could see there was a large missing ET because the lowest supersymmetric particle was considered to be behaving like a neutrino. And the other thing you notice is a fair abundance of B quarks. And that actually told us that we should be putting pixel detectors. So the pixel detectors were brought into these general purpose detectors, not for B physics, but for making sure that supersymmetry could be actually looked at. Of course, it does very well for B physics as well. Now, the other thing that we were considering at that time was extra higher gauge groups, which would then predict Z primes. And Z primes at the mass of about order of a TeV. So if it did exist and you found it in mu plus mu minus or E plus E minus, then you would actually need to know in which context that Z prime boson was sitting, what was the theory behind it. And for that, we needed to know, to measure the angular distributions. And for that, you needed to know the sign of the muon or the electron. And so that meant you needed to measure the momentum resolution of these muons would be at the level of 10% to allow you a 3 sigma measurement of the charge at PT of 1 TeV. So you needed a high bending power. So those are the kind of constraints that were being put in from the physics itself. And then you went into the detector design. But before I get into the detector design, I think this was shown earlier by Vivek. This is a slide of the timeline. And I think what I wanted to pick up was this 1990 workshop, which actually presented the physics state, but also the detector state. What sort of detectors would be able to survive in the high luminosity hadron collider, which Rubio's committee had actually suggested as being the next move for CERN. And it was at that meeting that we first started thinking that maybe it was possible actually to do the experiments at the 10 to the 34 luminosity, because it was much, much higher than what previous experiments had encountered. And then the various concepts were presented in 1992 in Avion. And from there, the 3 letters of intent were submitted, and 2 were selected by LHCC, CMS, and Atlas. And the technical proposals were approved in 94, and the construction approval at a cost ceiling of 475 million Swiss francs was set in 1996. And the construction really began in 1998, and it finished in 2008, so it took about 10 years. And in 2012, we discovered the Higgs boson. Now, coming back to the issue of the challenges, I mentioned working at 10 to 34 is not a piece of cake, and I think it was a prevalent feeling in the 1990s or late 1990s. We think we know how to build a high energy, high luminosity hadron collider. We don't have the technology to build a detector for it. So when you see these detectors working very well, you have to bear in mind that we weren't sure that what we were doing was going to work. Now, the reason is that there's a billion pairs of protons interacting per second. And at the high luminosity LHC, which we'll encounter in the next decade, this number will increase by a factor of 5. The large particle fluxes means there are enormous numbers of particles going through. The detector, which you all need to measure, we need to measure all of them. And that means the occupancy has to be low. That means the number of channels has to be very high. That leads to a very large data rate. 40 terabits per second, and now 200 terabytes per second at the high luminosity LHC. And finally, the one that really caused some difficulties was the high radiation levels. And these had not been encountered in our field before. And so what we had to do was to push actually whatever existed to its limits, and you had to innovate and look for novel solutions. And since the budgets were rather limited, then we had to use the industry and a lot of automation to drive the costs down so that we could actually build the detectors that could do the job. And for every sub-detector that you see existing in the current experiments, about 3 others were tried, taken up to R&D prototyping test beams, and only the ones that were likely to give you the results that you were looking for were retained. Now, the schematic design of a HEP detector, certainly for hadron colliders, is a very simple concept. It's sort of a cylindrical onion, and you have technologically advanced detectors in 4 principal layers, and each of these layers is designed to perform a specific task. And together these allow us to identify and precisely measure the energies and directions of all the particles produced in the collisions. So in that sense, the mission statement is very simple. but getting it done in practice is a bit more complicated. And the four layers are the inner tracker immersed in a magnetic field, electromagnetic calorimeter, hadronic calorimeter, and the muon system also immersed in a magnetic field. And the pattern of energy deposits left by the individual particles allows us to identify what the nature of that particle is. So let me start the issue of design. So the first thing you have to do is to understand what kind of magnetic field you would like to choose for muon identification and measurement of their momenta. There are several possibilities. For example, one could have followed Aleph Delphi Opal, the L3 experiments, where the coil sitting between the electromagnetic and the hadronic calorimeter, and the return field would be large enough to give you magnetic field in the muon stations. This would be cheap, but it's limited to low multiplicity and low rate. And it has this nasty feature of ECAL and HCAL coil interference, because the coil is pretty thick. So at the hadronic shower maximum, you're putting 1 lambda dead material, which is not a good thing to do. The second possibility is to use a toroidal system for measurement of the muons. Then you need to have a solenoidal system, which you could put in before the electromagnetic calorimeter starts, which is a choice made by Atlas. And they chose, here you could choose to put an iron core or an air core, and Atlas took the view of the air core, especially for measuring the momenta of muons at very high PTs, which I indicated is one of the design goals. Now, the third choice is actually the one that CMS took, where the coil is put after the calorimeter, and the coil is strong enough, large enough bore to accommodate calorimetry plus a tracking system, and only the muon system is outside, and the return field is enough to saturate about 1.5 meters of iron, which allows you to put 3 to 4 stations in there, which is considered to be rather important by CMS. So that was the choice made by CMS. One of the properties of the solenoid is if you return all the field that is generated in here, so you go in the field goes inside into paper here and out of the paper in the muon system, then a muon which would bend before the coil and starts unfolding the bend, it would point back to the primary vertex because high momentum, the energy loss is not terribly important. And that was quite an important property, because the sagitta, instead of being measured in the middle, for example, if there's a tracker, you'd measure the sagitta here, it's measured at the extremity of the inner tracker. And that gives you a much better momentum resolution, which is shown here. For example, the black line is much better than what the inner tracker does or the muon system itself does. And even combining it gives you a better measurement because of this fact. And also the first point, measured point, is for free because it's a high precision 15 micron point, which is because the bending occurs in the right plane. So there were quite a few advantages of the solenoid, and that's why CMS chose that. Now, CMS is called a compact detector, and the reason is that if you put the detectors people were talking about at that time on the same scale, then CMS looks quite small, and that was the reason for using compact. Now, the design objectives then were quite simple: very good and redundant muon detection system, best possible E-gamma calorimeter, high quality central tracking, and it should be affordable. And this is what it looked like 16 years later. And so the distinguishing features, for example, now concentrating on CMS, it's a single large bore high field superconducting solenoid, inner tracking, which is fewer but high precision measuring points, because it's all silicon tracker, which for example, Atlas is also now moving into that for the upgrade. An electromagnetic calorimetry with density scintillating crystals for the Higgs to gamma gamma, and the muon system, multiple 4 stations to give you good geometric coverage, meaning that 3 stations out of 4 should always fire, regardless where the muon goes, and 2 complementary technologies to make absolutely certain that the muon system will not need to be tampered with, improved as we go along. So those were the main things that drove the design. And also CMS took the bold decision of only having 1 hardware level of trigger, and the high level trigger was done in a CPU farm. And that is again a thing that people are moving into in the other experiments as well. So these were high risk, high return options that were taken. Now, let me come to the superconducting magnet. So the idea is, as I mentioned earlier, to measure 1 TeV muons with less than 10% momentum resolution. And in fact, you can see it here that at 1 TeV, we were actually expecting something like 5%. So we were fulfilling that goal. And to give you an idea of the challenge of the CMS solenoid was that these were the solenoids that people had built so far. And the Atlas barrel solenoid sits here in terms of the kilojoules per kilogram of cold mass and the stored energy. And CMS sits way outside of factors of 10. So this is a real challenge actually to make the CMS solenoid. And it took a lot of effort and a lot of expertise actually to get that done. So just this gives you an idea of the superconducting cable. It's really a plate, in fact. It's a 2 kilometer length plate. And it's a cut there. And there are 32 1 millimeter wires, and each wire actually has about 500 filaments of order of 100 microns of niobium titanium sitting in a copper matrix, and that's why it looks like a copper. And this was produced in Outokumpu. We started the construction of the magnet in 1998. And from the cables that were produced, then a Rutherford cable was made from the wires that were produced in Outokumpu. And this is a Rutherford cable being produced, which is a flat weaved cable, which allows you to cancel the eddy currents. So this was done in Brood cable work near Zurich. Then the cable was co-extruded. This cable was co-extruded with pure aluminium alloy, pure aluminium rather, not alloy, which came from Sumitomo in Japan. And this was done in a company called Nexans near Neuchâtel in Switzerland. And the forces, the 4 Tesla gives you about 60 atmosphere outward pressure, which has to be taken up by the coil. And so the cable had to be reinforced by electron beam welding with two plates of high tensile strength aluminium alloy. And this is the process of the electron beam welding, which was a company near Grenoble, which was done. And then this is what the 4 layers of the coil looks like against a mandrel through which the liquid helium would go through to cool everything by conduction. And so this was the cable was 2 kilometers perfect length was sent to Ansaldo in Genoa, which then wound the coil in 5 pieces. And those 5 pieces were then shipped from Genoa to Marseille up the Rhone River and carried by truck to CERN. And these are 5 bits of coil, the 4th one going on here, as you can see. And then after insulation, the whole thing was turned horizontal and went into the outer vacuum tank. And then the inner vacuum tank went, and you welded all of these pieces to make a coil, to have create a vacuum inside. So this was a process which, as I mentioned, the state of the art. And this is the coil is now sitting here, as you can see, and this is a transverse cut photograph of the experiment in 2008. And you can see the inner tracker. The first layer, the second layer is the electromagnetic crystals calorimeter. The third layer is the brass scintillator calorimeter. And on the outside, you can see 4 layers of muon detectors. And these are drift tubes. They are in the barrel region. And you can see a lot of complication. And there are many, many countries that were contributing. This piece here, for example, these little slices there that you can see all over were made in India TFR. And they are the Indian responsibility that is shown on this particular slide. There are other contributions as well. So you can see that, for example, if I just pick this was this layer was made in Aachen. The second layer was made in Madrid. The third one is in Padua. 4th one was in Torino. And the cabling was done by Russian and Bulgarian teams. The cooling pipes were put in by Polish teams. The green structures are from the UK, and the support structures here are from Pakistan, and so on. So you can see in one picture, just looking at the muon system, there's so many countries involved. And the other thing to remember is that there are a lot of PhD students, about 1,000 PhD students in each of the CMS and Atlas experiments, and about 4,000 scientists from over 50 countries in each one of them. Now, let me go to the inner tracking, and so give you an idea of how one goes about designing the inner tracker, for example. So this is a plot. On the left-hand scale, you see the fluence. So this is over 10 years. From there, you can actually work out the rate itself, and from there you can see if you want to keep an occupancy. If you have pixel detectors, you want to have an occupancy of 10 to the minus 4, and that's the only thing that would work because the flux is so high, 410 to the 7. If you go to 20 centimeters, the flux is going to be correspondingly lower by a factor of 10, since you're 3 times 3 squared down. And then you can use silicon microstrips with an area of about 10 millimeters squared, 100 micron pitch, 10 centimeters long. If you go further away from the beamline, then you can have silicon or gas detectors as such. So if you had silicon sensors, as we have in CMS, to keep the same occupancy, you can double the pitch and double the length of the strips to keep the tracking count down. Now, so what did this give? Now, this is again a slide from the early 90s. You can see there's a lot of mess here. So it looks like you can't actually do much work when you have events like this. But what you notice is that there's very little stuff going on the outside, because the 4 Tesla field actually means that only tracks with more than about 750 MeV can get to the outer parts. So the outer parts are rather clean. And if you were able to measure each of the particles, which is one of the design goals, and then you put a limit of 2 GeV-PT, then this is what the event would look like. Now it looks much cleaner than the one that you see above. And that was the reason why we chose the all silicon tracker, because it allows us to pull out events of this nature. And the other thing is that if you have 10 centimeters length, so you can take a slice of 10 centimeters on here and project it onto the transverse plane. And now you see very many fewer tracks than here, and that actually helps the pattern recognition. So these were the types of considerations we were looking at when we were designing the inner tracker. And this is what the inner tracker looks like. And so you have the pixel detectors in green, the inner silicon, the outer silicon, and the end caps in the barrel region, and so on. This is the barrel region. Now, to give you an idea of I mentioned that it wasn't obvious that we could actually do these, make these experiments function. And so one of our first meetings, Lorenzo Foa was our main referee from LHCC, and he asked a question for both CMS and Atlas, by the way. And it wasn't even a question 1, it was a question 0. So the question is, what can your electromagnetic calorimeter do in a standalone mode if you have to switch off your inner tracking because of excessive rate? So that was the feeling at the time, that you would have problems. So what would you do if you did have problems? And of course now we have pixel detectors which are 3 or 4 centimeters away from the beamline, but that wasn't the case in the early 1990s. And so in our response, we said we don't think that we would have to switch off the whole inner tracking for the reason I mentioned to you earlier. The outer regions of the inner tracker are rather clean, so we didn't think we'd have a problem. So that's how we responded. Of course, we did much better than that. Now, just to give you an idea of the technologies that we were considering at the time, to make sure that the one that we chose would work, we actually looked at scintillating fibers, MSGCs, silicon pixels, and microstrips. And the silicon technology was ideally suited to the LHC requirement, but at the time, the radiation damage was poorly understood, and the cost per unit area was very large, and the large number of channels would be required. And so it wasn't obvious that we could actually use that. As time went on, the radiation damage got properly understood, and we understood that we had to keep the detectors at minus 20 degrees to arrest the radiation damage. And the cost actually was coming down, and we moved from 4-inch technology to 6-inch technology, which actually allowed us to make the whole tracker with all silicon. And the number of channels is 10 million channels. So this actually, technology actually evolved in a favorable way for us to make that decision towards the end of the 1990s to go to all silicon. So the other thing which was important was to make sure that the electronics would be radiation hard. So this is a picture of one of the chips. So these are this is a silicon module in the outer tracker. So they're about 500 channels, 200 micron pitch, and each one of them has its amplifier, its pipeline, and it's some circuit which allows you to localize the charge into the right crossing. And then you need to send the data out, and it's done by light. So the pulse height that you extract modulates a laser, and the laser signal is sent out on an optical fiber to the services cavern in an adjacent room, which is separated by 7 meters of reinforced concrete so that we can work in there while the machine is operating. So the first thing you have to do is turn light into an electrical signal through a photodiode and then digitize it. And then you do some processing to zero suppression and things like that. And then you send the data on about 1,000 fibers to the surface control room, which contains a computer farm of 50,000 cores. Now, one of the problems we had actually was that in 1999 or 97, we were ready to go into production for the chips. But it turned out the vendor decided to produce this chip in a new foundry. And it was clearly a commercial decision because we're not very big players in this game. The big players are the computing industry and the gaming industry. So we can hardly even go one per mil. So the vendor actually decided to move to a new foundry, and they lost the ability to make radiation hard chips. So we were thrown back to zero, essentially. We couldn't use that technology, we couldn't use that design. So we had to find a new technology. And this was, the experiment was supposed to start in 7-8 years from that moment. And so we were able to actually face that problem because it turned out that somebody had gone to the States and the quarter micron technology, which was the one that was being used for computing industry, the finest feature size, actually could be made radiation hard with a few tweaks. And we did that. So it was a very risky decision because some of the colleagues said, this will never work and you're taking a huge risk with the experiment. But, we had to do it. It turned out that this technology actually was really, really well suited to our purpose. It's at lower cost, faster turnaround with design iterations, lower intrinsic noise levels, and lower power consumption. You couldn't ask for more. And so riding technology waves allowed us to contain costs in an area that carried very high risk. So in a sense, the long duration projects have to be aware of how the technology evolves, so to take advantage of those possibilities. And it turned out that even if we didn't need radiation hardness, this technology was so much better than any other that we designed chips for areas which we didn't require radiation hardness in this technology, the quarter micron technology. Now, going back to the electromagnetic calorimetry, at that time there were two possibilities that we were looking at. One was a high resolution calorimeter, and the other one was a slightly worse resolution calorimeter at the level of 2% or 10%. So you could see the difference of what a Higgs to gamma gamma peak would look like with 500 inverse, with 100 inverse femtobarns. And you can see that it'd be much cleaner if you had 2% rather than the 10%. So that's what we did. And so, again, this required quite a significant program of R&D and prototyping to get to this point. So the idea came up in 1993 to use lead tungsten crystals. I was shown a few samples somebody pulled out from his pocket, from his handkerchief. They looked pretty yellowish as a few centimeter cube samples, and I didn't think that would ever work because so much effort would have to be put in there. But then in 1993 or 92, we went, 93, we went to Kharkov, to the institute that is currently under a bombardment to a certain extent, as you all know. And there was a lady who showed was growing crystals in her basement in that institute, and they had shown some results, very promising results, with a very good energy resolution in a matrix of 9 crystals read out by photomultipliers. So that suggested that that would be a very interesting crystal. So a lot of work had to be done to improve the radiation hardness. So that is done by improving the purity by changing the ratio of the lead oxide to the tungsten oxide, and removing any defects by doping the melt with some other chemicals. And the prototyping required going into test beams to check everything. And one thing we noticed was that it had a pretty severe temperature dependence, so we had to stabilize the temperature. And then introduce mass manufacture. So you had to figure out the companies, and mass manufacture took place in Russia. At some point, Russia joined the WTO, World Trade Organization, couldn't subsidize energy and the prices any longer. So the prices actually doubled on us, tripled on us. And so we had to sort that out. And that required intense diplomatic discussions with the CERN DG and the Russian Minister of Science and Technology and so on. So there are lots of technical, diplomatic, and other kinds of issues that cropped up, which we had to resolve, and also get a second manufacturer, for which we had to borrow 10 million's worth of platinum from the UBS vaults in Zurich and send them to Shanghai and get them back and back into the vaults and so on. So there were all sorts of things we had to do. And the systems integration, installation and commissioning in 2007 and 2008, and data taking. Now, in the passage, this was the sort of readout that I mentioned that I saw in Kharkov, and looked very nice. So I thought, since we are in a 4 Tesla magnetic field, we couldn't use photomultipliers. We would stick in silicon photodiodes. So when we did that, we took the result, and this is what we saw. This is not a calorimeter. It looks like lots of particles going through the silicon photodiode, depositing a lot of energy. So we had to actually figure out a device which you could get gain, and that was an avalanche photodiode which just come out. People had just started experimenting in 1993, 94. And there are a few samples which are available. We have 150,000 of them in the calorimeter now. And there you can see the calorimeter, something which resembles a calorimeter, very similar to this thing here on the extreme left. So it took a long time, took about 10 years of production. So this is each crystal boule takes about 3 days to grow. And this is Roger Cashmore looking at it when we open that. And you need to then cut it, polish it, and depolish one face to get uniformity sorted out. There are 10 crystals there, 400 crystals, and then 1,700 crystals. And the electronics and the cooling systems are going to go into this thing. And after about 7-8 years of work, this is July 2007, where the barrel has been installed. Now, I won't say very much about the muon system. The main thing was to have 4 muon stations, because you can see that you can't actually, you always have gaps, and you had to make sure that the gaps were not lined up, so that you always had 3 stations which would fire. And we wanted to make sure that each station could actually measure the angle as well as the direction. So there were actually 8 R5 measuring layers and 4 Z measuring, because you also need to measure the in the Z direction, and similarly for the end caps. And so this was also a challenge, but challenge was more the large area that had to be covered rather than the technology itself. And this is the triggering and data acquisition system. I won't say very much about that, apart from the fact that it has one hardware level. Now, when we actually had tested the magnet in 2006 and slices of the experiment on the surface, we had to take everything down, because the experiment was essentially largely assembled on the surface, and large pieces were taken down. On the surface, you had a lot more room, and so you could actually work on many areas in parallel. Downstairs is a lot more limited, so that was the decision that was made early on that we would slice this cylinder, the cylindrical onion, into 15 slices essentially, and we'll take them down one by one with a lot of the detectors already mounted. Here you can see the coil is bald, but you can see the muon stations are all in there. There's some missing here because that's where the point of lift is attached. And then this was the actually February 2007, and this is the piece now going down. Oh, sorry. Okay, I did something I shouldn't have done. Now it should start. Yeah, okay. So you can see that the cover plate is retracted. This thing is lifted by a crane on the outside, and it's starting to go down. The thing was dark, and you can see now light. So it started the operation at 6 o'clock in the morning, and about 3 o'clock in the afternoon, we actually landed on the underground cavern's floor. And during that time, there was a fire alarm, and we had to stop all the operations. And the whole thing had to come down very straight because if you notice here, there's very little room on both sides, one hand's worth of space. So if there was any tilt, it would block and we would not have a detector. Now you can see this is pretty bald. And about 7 months later, the thing looked like, sorry, I should move. So 6 months, 9 months later, 6 to 9 months later, that bald coil is now full of cables. And these are all of the cooling pipes, the high voltage, low voltage cables, signal cables, and the cooling that is needed to bring the tracker down to minus 20 degrees with their cladding, you can see. Not much space was allowed for that. So, and all of this had to be connected correctly because to get back to this state takes about 6 months of opening. So everything had to be done as if it's going to be sent to outer space. And this was the detector closed in 2008. To give you an idea of the scale, there's a person there on the floor here. So this gives you what the experiment, CMS experiment closed looks like, which is the situation today. Now, let me just sort of summarize a little bit, especially the challenges. So it took about 20 years from concept to the end of construction. And as I mentioned to you, we pushed the limits of several technologies. In terms of engineering, not only civil engineering, because that was also a big problem to get that cavern dug 100 meters underground with the shafts there. There's an underground sheet of water at minus 40 meters from the surface coming from the Jura to the lake. And it's pretty strong currents of water there, which you had to drill through. And the magnet was a state of art. Instrumentation, there was quite a few novel detector technologies, and they're giving you some idea of that. And also the low-cost radiation-hard electronics, giving you some idea of that. I haven't talked very much about the data acquisition fabric and the selection of events, and also the worldwide LHC computing grid, both which were necessary to get to the results that we have at the moment. We have about 1,200 publications now in CMS, and that required all of these things to be working perfectly as well. And again, to build all of this stuff required a worldwide collaboration. You needed the resources and the talents of people all over the world to actually arrive at the detectors that are functioning so well. And of course, the distributed analysis. And as you probably know, quite a lot of analysis is also done in India of the results we take here. Now, this is what India and CMS, so they've been founder members since a long time, some following on from L3. And in the detector construction, we already pointed out the hadron calorimeter. There's also a silicon pre-shower, which you can't really see, which has sensors which were made in Bangalore. And of course, in operations, they are participating even today to make sure that everything is maintained and running. And in physics, and also in the upgrades now, which I'll say a few words about later towards the end of the talk. So they have wide responsibilities and across the board as well. Now, let me go quickly to the science itself. Now, the first thing after having built the experiment, as I mentioned to you, it wasn't obvious that we would be actually able to do the physics we wanted because some of the technologies had never been made before. It is also true that after the accident in 2008, we took a lot of cosmic ray data with the magnet on and the experiment fully functioning. And the data told us that the experiment would function pretty well, although there are a few things which we needed to sort out to be absolutely ready in 2009. And so within a few months, we actually did produce a lot of results. And the first results were related to this question: do the experiments perform as designed? And for that, you need to look at the momentum resolution, the mass resolutions, and things of that nature. And then you start addressing, is known physics correctly observed? For example, do you produce the W and Z bosons as predicted by the theory from Fermilab results, jet production, and so on and so on? And only then can you look for new physics. And I'll give you an idea of how well we did. So the next slide here is the Daimyon Spectrum. This is now in 2010. So this is 40 inverse picobarns of data. It's about a month of data in 2010. And this is the Daimyon mass, and there's a number of events, and you can see a very nice spectrum. So these are the resonances we all familiar with in the 1960s, the J psi and upsilon, J psi prime in 1974, the upsilon and upsilon double and triple prime in 1977, and the Z boson in 1983. So let me concentrate on this one here, because that is what we were looking at. So we were designing the experiment that the upsilon peak would have a mass resolution of 70 MeV. So that was the design goal. Yeah.
Yeah. So you have about 10 minutes now.
Yeah, I should be finished. I did start a little bit late, I think. So
Yeah.
I might take 12, 13 minutes, but anyway.
Okay, fine.
So the what we measured was 67 MeV. So there were distributions of this nature and their efficiencies and all sorts. So there are hundreds and hundreds of plots, both in Atlas and CMS, which people looked at, and they're all actually indicating the experiments were working extremely well, which was a minor miracle as such, because it wasn't obvious that such complicated experiments could start so quickly. Now, the other thing to look at is the physics. Is known physics correctly reproduced? Now, here's an event, one of the early event displays. You can see clearly here an event which has many jets in it. I mean, you see collimated bunches of particles. So this is the yellow is the inner tracker, red is the electromagnetic calorimeter, and blue is the hadronic calorimeter. There were no muons in this, so you don't see the muon system, which usually appears as green, appear in this plot. Now, what you can do is throw a cone around here, like what people expect QCD, measure all the particles and the energies, and you then have the angle, and you have the PT, and you plot the angle and the PT. This is the PT and different angular ranges, the different lines, and see whether they agree with the QCD predictions. So this is 34 inverse picobarns, 1 month after data taking started. And these are the results that were being produced about a couple of months afterwards, after the start. And you can see the data and the Monte Carlos and QCD predictions bang on. So not only were the QCD predictions being reproduced, but also the Monte Carlos actually were functioning well. So the whole thing actually was a very, very pleasant surprise. So then you go and look for physics beyond known physics at the time. So we were searching for the Higgs boson, but also searching for the physics beyond the standard model. And here you had supersymmetry, extra dimensions, which I mentioned, and any other unexpected physics. We haven't found any significant evidence for beyond the standard model physics yet. So let me just quickly look at the Higgs boson. In fact, the Higgs was first seen in CMS because he came to us in 20th of October 2008, before he went to that afternoon to Atlas. Now, this is what the Higgs boson looks like, a candidate event in CMS for the gamma-gamma channel. So you can see the types of events that I was mentioning to you. If you put PT cuts, so here there's no PT cut, so this is one relatively clean event. And you can see the 2 photons, and the height is actually the energy, related to the energy. You make the effective mass and you get a peak. And here is the Higgs goes to ZZ star into 2 electrons, shown here, and 2 muons. And now here you can see the muon station singing and the event in itself. So now LHC is also a factory of standard model particles like the B's, the taus, the W's, and Z's, and now the Higgs as well. So that is what we're going to be looking at for the high luminosity LHC. So this is the seminal paper that was published in 2012, and this is a message from Tom Kibble, Argen Guralnik. This is a triumph for the standard model particles, but even more for the experiment. So they actually acknowledging the work that the experiments have done. Now, we all know that there is a lot of evidence for physics beyond the standard model, and I just pick up 4. I could have added dark energy as well. So I think this is to indicate that the physics ahead of us, or the problems of the standard model, are, I think, as profound as the problems of early part of last century, which then led to the advent of atomic physics and quantum mechanics as such. So I think we're living in, although we don't really know what the path looks like, the questions we are asking are just as profound. So this then leads me to the possibility of extending the life of the LHC to actually accumulate more data, get more precision on whatever we're measuring, and perhaps be able to unfold something. So this is the strategy from 2019. So the topmost priority is the exploitation of the full potential of the LHC. Now, when you look at extending the life of an experiment, there are 3 considerations you have to make. Can you get a higher center of mass energy? In our case, it's unlikely because you only got half a TeV left to cash in now from what we're going to get this year. The other thing you can actually is to take a lot more data. So we want to collect 10 times more data. So that will happen. And the third thing is actually you make qualitatively better detectors. So although I indicated to you that it was quite difficult to understand that we would be able to make the detectors we were discussing at the time function as we wished them, but they have, and they function better than we expected. I think similarly, we are making detectors which are better than the original detectors, and they're also carrying risks. So in that sense, I could repeat the statement, not absolutely certain that they will work, but on the other hand, the experience suggests that they should. And so again, the thing to look at is what is the physics thrust? And the physics thrust is actually the Higgs boson. Now we will get 10 times more Higgs bosons. So that means that we will be able to make precision measurements of the properties, and as was being discussed in the previous talk, perhaps approach the 4-5 sigma level of the self-coupling in this new sector, which then will give us information about the Higgs potential, which is a key thing to have to understand the mechanism itself. So it is quite an important thing to actually do. Now, of course, theoretically, the questions will also be that can one make prediction of the level of percent? And of course, the idea of continuing looking for physics beyond the standard model, and also the precision of sensitive standard model measurements, because I think there is intrinsic value of knowledge acquired independent of discovery, because they may be anomalies which crop up, and then they need to be addressed. So this translates, and I'm not going to go into the details, and you just look at the red lines. So we need new, higher granularity, more radiation hard inner trackers. So in the count will go up by another factor of 10, the data rates will go up by another factor of 10. And you replace components which are affected by radiation, especially in the end caps. And you need to have a more selective trigger and a higher bandwidth data acquisition system, so you acquire more data. You write more events on tape, but they are even more selective, because you're bringing the track triggers into the level 1, so they will improve the quality of the data that you record on tape. It will have a higher physics content. And the replacement of front-end electronics, because the pipelines have to get longer, because we actually use more time to make a finer selection of the events. So that improves the physics quality, if you like. And the other thing is, since the pileup would be very large, introducing precision timing allows you to take a snapshot of the level of 100 picoseconds of timing to select the right event and discard all the tracks which are not from the event of interest. So now, last 3 slides, I just wanted to recall again some of the problems. So we had to redesign the tracker front-end electronics. We had to change to all silicon tracker in 1999. We were supposed to start in 2005, by the way. And we had to redesign the ECAL front-end electronics in 2001. And there are many issues which are related to production issues of the silicon sensors, the crystals, which I've indicated, integration and installation. And we had to re-engineer, which is not something which I've gone into, the reconstruction software in 2005 and prepare CMS for physics extraction. And that was an exercise which is not, we don't speak about it, but it took a lot of time. And we had to train physicists actually to do the software, to understand the software and do the analysis in good time. And another thing that we actually were not thinking at the beginning was particle flow reconstruction. So our hadron calorimeter was relatively weak compared to Atlas, but the particle flow reconstruction meant that the performance was extremely good. Now, the reason for raising these challenges is that we are going to expect challenges in construction of the phase 2 detector. And this is really a call to the PhD students. If you're not already working on hardware, join in, learn about hardware, and become rounded physicists. Because if you understand the defects of the detectors, then I think you do better physics. You have a better understanding of whether something is going wrong or not. Now, what I wanted to end up with is this slide here, which is Atlas as a similar slide. What you see here are measurements of decay modes, which we didn't think we would be able to make when we were designing the experiment in the early 1990s. So, for example, our technical proposal did not include the search in these modes, the BB, the tau tau, the WW, or the mu mu. And yet they are on this plot now. And that is at a level of 130, 140 inverse femtobarns. Remember the plot that I was showing you was 100 inverse femtobarns. So we never thought that we'd, and that is a testament to the quality of the detectors, because they were much better than we had expected, because there's plenty of margin in the design. And that's another lesson to remember, that there should be plenty of margin in the upgraded detectors to enable you to do more physics than you thought was possible. So let me summarize. The Lhc experiments, both all the experiments plus the accelerator, had to overcome many challenges, and I've indicated some of them. The existing technologies had to be pushed to their limits, and the new ones invented and developed. And the accelerator and the experiments have performed much better than the designers could have dreamed. The Higgs boson was discovered much earlier than anticipated and seen channels that were thought impossible. But it appears to be the one that is predicted by the standard model. And so we're now studying it in great detail. And hopefully we will get more information about its nature, and possibly through the self-coupling get some idea of the true nature of the potential. We haven't found any evidence for new physics, although there are hints. But the other thing to remember is that we are talking about getting 3,000 inverse femtobarns, and we're looking at about 150 at the moment. So there's a long way to go, and maybe we'll have surprises along the way, and hopefully so. And so the question is, what further discoveries await us? And as I indicated to you, several of the open questions today are just as profound as those a century ago. And the LHC does remain the foremost place to look for new physics. Of course, it's not the only place to look for new physics. There are many others, but it is perhaps the foremost place. And the last thing is for younger people, it's only the experiments reveal or confirm nature's secret. So we must continue doing experiments. Otherwise, our discipline will become metaphysical, I suspect. So let me finish here, and thank you for your time.
Thank you, Professor Viddi, for this excellent talk. And I think many of the things and the challenges that the CMS faced during this long period of planning and construction, you brought out very nicely. So now it is open to all for the questions. Please raise your hands so that I can call you up for the questions. I don't. Do I see the hands? I see quite a few hands going up already. So from the room, TIFR D406.
Yeah. So Jim, can you hear us?
Yes, I can.
Okay. So this is related to when you said about the CMS and Atlas. The complementarity and in terms of technology of the starting from the magnet to the tracking and the calorimetry, right? I mean, so now if I only focus on the inner tracking system, one going for entirely silicon versus this combination of this transition radiation and then silicon partly, and now they are going for fully silicon thing. So at the hindsight, do you think like when this decision was made, I mean, since you are talking of the very in very nice way, I just wanted to say that what was going on the CMS and the Atlas side, they wanted to be different because complementarity, or why the silicon thing was not tried by them, or rather CMS didn't think along the way Atlas was thinking. So what was that sort of the clinching thing that led the CMS to go for silicon vis-a-vis Atlas system?
I think this
Okay.
addresses an issue which I didn't touch upon.
Right.
The people who were designing CMS had the experience of UA1, and the ones who were designing had experience from UA2 did not have a magnetic field, and UA1 had a magnetic field. And we had learned that if you, for electron identification and the measurement of their energies, use momentum over energy match and discard many of the pions, for example. So it's pi e separation. So the magnetic field was quite important. So we never considered a concept without a magnetic field, and we never considered a concept with a transition radiation detector or a pre-shower in the barrel region. For those reasons, because we had that experience from UA1. And experience also informed us on the difficulty of the muon system. So that's why the muon, the M stands for the muons, because we were wanted to absolutely the muons would work, because we had not a terribly experience. And certainly the system that we had would not have worked, because we needed to measure the momentum of the muons, because the muon was so large that we would never be able to select them just by identifying a part of the muon system. We needed it on it. So there are features of that nature. And the other, we felt that the pattern recognition would be robust if we had 10 to 15 points, but well measured with an accuracy of 15 microns. Whereas the approach taken by people in Atlas was that not only did they need these precision points, but they also need a large number of points. That's why the straw tracker came in, because that gave them 20, 30 points. And didn't feel that we needed them, and our simulations were telling us we didn't need them. And that has turned out the case. And I tried to give you some impression of why that would be in the way I described the inner design. So I think it comes from the taste and the experience of the designers. And I think it is good that we ended up with complementary designs, but we did not set out in that fashion. So, for example, it would have been very difficult for CMS to accommodate a cryogenic electromagnetic calorimeter. You can't have a cryostat for electromagnetic then a hadron calorimeter, then another cryostat for a solenoid. It's not elegant. So some of these things happen naturally, but I don't think people were thinking of that at the time. But it is good that there is this complementarity that you point out.
Orno?
Yes, can you hear me?
Yes.
Yes.
Thank you for the nice talk, first of all. And okay, so one of my question is already asked by the previous person. So I was also concentrating on the magnet system. So my question was also related to magnet system. Is that, I mean, was the choice intentional that it has to be different, or it was like the test of the collaboration or the people who has thought about the experiment initially? It was based on that. And you already said that it was probably not intentional to be different.
Yeah, I think the again part of the answer lies in the experience, and UA1 had a dipole field, and the dipole field would not be a good choice because CDF had come up online, and they had a solenoid, and the solenoid gave good results, and so the problem for us was to actually understand whether a single magnet could do the functions of the inner tracking in the muon system. And indeed it can, but it has a very large bore and a very long length. So the solenoid it was 15 meters long originally, and it was cut down to 13 because of the cost, to accommodate the cost issue. But the bore was 6 meters in diameter, and that meant that you could actually, because the idea there was the bore was not really necessarily to you could accommodate tracking and calorimetry inside, but it's also enough field because it's dl squared, which then has to be returned in the iron, and that iron has to have a thickness about 1 meter 50, so we could accommodate 4 muon stations, and so that actually dimensions, and then we found out that the inner tracker and the calorimetry can easily fit in, although in the barrel region it is relatively thin, and this is where the first scintillator layer that I indicated you made in TFR plays a very important role, because it catches any energy that is leaking or particles leaking from the hadron calorimeter, which is not 10 lambdas inside the coil. There were things, so the solenoid field and the bore was chosen for those reasons. And the outer diameter, by the way, was chosen by the fact that we did not want to destroy any bridges or buildings when we transported the coils from Mâcon to Geneva. So there is a picture where I have 10 centimeters on either side of two buildings, and the coil is going through it by road. And so if it'd been bigger, we would have had to destroy things and rebuild them. So that was another constraint, the peculiar constraint.
Yeah, and the other question that I wanted to ask is that obviously we have seen the fascinating results that we had from CMS Run 2 and Run 1. But is there any drawbacks in the design that you think could have been done differently so that the performance could be better than what we had?
I think if you'd asked me that question in 2005, I might have responded that the hadron calorimeter might have been better. But with the advent of particle flow, which actually relies heavily on the fact, which we weren't aware at the time, but relies heavily on the granularity of silicon tracker and the fine granularity of the electromagnetic calorimeter, which separates out the energy deposit very cleanly, which allows particle flow to function properly, and it then sort of improves the jet performance enormously. So I think in the thing that I can say is that if you look at the FCC hadron collider experiments, they are very much similar to what CMS is.
Yeah,
I think if there was one thing, we perhaps could have coiled a little bit longer, but on the whole, I think the concept is stood the test of time quite well.
Okay, thank you.
Professor Sunandu Banerjee, I can see.
Nanda?
Yeah, the thing is good. It was a very nice talk. Okay, I think, okay, this well, regarding the complementarity of the experiments, okay, I mean, I think LHCC is maybe they make the key role. Okay, I mean they couldn't have chosen two proposals which are built on building the identical detectors. Okay, so anyway, that was just a side comment. I have a question. Okay, I mean, wasn't cerium fluoride considered at the beginning as a crystal?
Yes, it was. So I think the LHCC wasn't given a choice. Coming back to the first point, because they had Atlas and then they had two concepts which were based on solenoids, the Samting's 3P and ours. So they didn't. So Atlas was going to get approved anyway because it was a combination of Ascot and Eagle. That meant that the choice the LHCC had to make was between CMS and L3P, and they chose CMS partly because of the elegance of the design, not necessarily because behind it were, there were essentially nobodies. But coming to the question of cerium fluoride, yes, that was considered, and a lot of effort was put onto cerium fluoride. And the lead tungsten was a side active sense. And but the which you actually made sort of go ahead of cerium. One, it was its density. The radiation 0.9 centimeters compared to 1.7 correctly of cerium fluoride. You would have to have twice the length of crystals, and the length of the crystals means high. And also, it meant that you couldn't actually make them in one go. You'd have to cut them, so you'd have to have two crystals, and then either glue them, and then the gluing process would introduce all sorts of difficulties, or you had to read them front and the back, and its own problems. So it wasn't a very easy technology to deal with, although it could have done the job. So that it was dense. It could do the job. It had difficulties, which I mentioned. It has a temperature dependence, but all of those would be overcome and were overcome. So in that, perhaps it was the right choice. I think cerium fluoride we would have cost a lot more and taken even longer to actually get done.
Yeah. No, I know the reasons. Okay, yeah, but it was just a question.
In fact, we also considered hafnium fluoride glasses, which could be in one go because it's a glass, and and shashlik. So there were 4 technologies we looked at.
Yeah, in fact, okay, at TF in those days, okay, we are measuring the radiation hardness of the glasses, the cerium fluoride, and lead tungsten crystals. Yes.
Yeah.
So also Shashlik.
Yeah. So shashlik was the. In fact, the plot that I showed you at 9%, that was the shashlik plot.
No, I'm saying that in TIF are also involved in the Shashlik design that time.
Oh, okay. Because I also personally worked on shashlik and the lead tungsten, but I didn't work on cerium fluoride.
No, we were doing radiation hardness tests for all these small crystals.
Sorry, Kajari?
Okay, so Kajari, could you repeat your comment? I think she mentioned that we were doing the radiation hardness tests regarding the calorimeter choices.
Yeah, we were doing these radiation hardness tests. At BRC, we were taking them to expose them to Apsara detector for the neutron exposure, and then for the gamma radiation, and then we were measuring the photon transmission in our photochemistry lab in TIFR. So that is early 90s, 1990, 1991, 92, etc. And of course, I don't know whether that was more under crystal clear collaboration. Prince Malhotra, etc. were also involved at that time.
Yeah, but I think by that Prince, it was 93, 94 probably, more like that. But anyway, so I have question for sorry, Ram, could you go ahead?
Jim?
Yeah.
Can you hear me? Yeah. So my question is like regarding this current crisis in Ukraine. So how is that going to impact the HGGAL upgrade project? Because I have worked with the Estonian group, and they say like this is going to like impact the HGGAL program like severely. to the point that it might extend the long shutdown, the next long shutdown.
What crisis are you mentioning?
Like they say that some primary contractors involved in the GCAL project actually belong to Belarus, Russia, and Ukraine.
Oh yeah. No, okay.
And the assembly unit was in Kharkiv, which basically does not exist anymore.
Yeah, the Ukrainian issue. Yeah, there are two aspects to it, or three aspects. One is the lot of Russian participation. The major part of the Russian participation for the phase 2 upgrades is in AGCAL at the level of about 8 million francs. But it's not only that, it's also the people. There's a lot of expertise that sits there, which has been working on engineering essentially, and also later on in terms of the installation and commissioning when it happens in 5-7 years. So it's not only money, it's also people. And all in all, it's going to cost a bit of money to actually, if something in June Council, where they're looking at the international cooperation agreements, which then actually set the scene for collaboration as such. So we would have to actually work out how to cover that those contributions from the Russian teams. We have copper tungsten plates, and I know that one of the things that is happening is to see if copper tungsten plates can be produced in India. Of course, it'll be the Western cost as such, and so on. So there are things of this. I think the AGCAL project is talking to all other participants, but also trying to see if it is remotely possible to continue, but too much negative consequences, put it this way. So I think people are aware of it. I don't lead the AGCAL project any longer, so it's the people like Carl Gill and the CMS management and the including funding agencies and council that are looking at this issue, because it affects the as well.
Thanks.
For the sake of
Okay,
time,
let us say,
let's go on.
yeah, I was going to conclude this part of the session. So thank you, Professor Jimbirti, once again for this nice talk and the interaction part. So let me
It's a pleasure. Thank you very much.
Okay,
A
thank
very
you,
good
Jim.
question.
Thank you, Jim.
Thank you, Kajari, for the
Okay.
invitation. Thanks. Bye.
Bye.
I'm going to
Bye.
sign off.
So
Okay.